Hi everyone, I'm going to work through a couple of the homework problems with you here today. The first one that I want to work through is section 1.7, problem number 17. Problem number 17 asks us, are the following functions continuous? And explain your reasoning. So I'll point out first of all that both of these functions, f and g, are piecewise functions. F of x is defined as equaling x when the inputs are less than or equal to 1. And f of x is defined as equaling x squared for all input values greater than 1. We know already that f of x equals x is a continuous function. It's a line, a linear function, they're continuous. We know for sure that f of x equals x squared is a continuous function. So the question becomes, what about at that point where f of x goes from being equal to x to being equal to x squared? In other words, what happens when x equals 1? Do I have continuity at that point or not, at that input value? So to check for continuity, the one thing I know is that if my function is continuous at a particular point, then the limit as x approaches that point has to equal to the actual function value at that input. So what I want to do here is I want to look at the limit. Well, I need to see, does that limit exist? So the limit as x approaches 1 from the left of f of x, what is that? So I have here from the left, f of x equals x. And so as x gets closer and closer and closer to 1, my output gets closer and closer to 1. And so that is indeed 1. What about the limit as x approaches 1 from the right of f of x? In other words, the limit as x approaches 1 from the right of x squared. Well, and I can see that as x gets closer and closer to 1, x squared is getting also closer and closer to 1, so that limit is indeed equal 1. So I know that that limit exists. Now my next step is to check and see what is f at 1. I go back up here to my rules. F at 1, I'm going to use the first condition here where x is less than or equal to 1. F is 1, x is 1, so f at 1 is 1. So indeed I know that this is true and I have a continuous function there. So now let's look at this on Desmos because I think it's really handy to look at the graphs of functions. So I'm going to come over here and I'm going to type in, well, if I have f at x equaling to, and I'm going to show you how to put in a piecewise function. So in Desmos, you use your curly brackets to indicate you've got a piecewise function coming up. The first thing that you do in Desmos is you give the conditions. So it's a reverse order of the way that we actually write them in the textbook or on our paper. We're going to give the conditions first and then the rule that we want to follow with those conditions. So I say x less than or equal to 1. And then the syntax here is to have a colon. And now I give the rule, and the rule is simply x. And you can see Desmos already graphed that part of the function. Now I need to enter in the second condition and the second rule. So I have a comma here to separate out my pieces of my function. The next condition that I have is where x, or I should say 1, is less than x. And I want to follow this condition. The rule that I'm going to use with this condition is x squared. Okay, so now I have my graph here nicely shown by Desmos, and I can see for sure that as I am approaching 1 from the left, the output is approaching 1. As the function is approaching 1 from the right, The output is approaching 1. Those were the first 2 steps I showed over on this screen over here. And for sure, when f is 1, my output is 1. And so by looking at the graph, I can see it's continuous, and I can show all of my requirements for continuity to be there. So yes, A is a continuous graph. So now let's go over and look at B. I don't know why that keeps popping up like that. Let's see. So when I go over and look at the second part here, this time, again, I know that when x is less than or equal to 3, I have a continuous function. If x is greater than 3, I have a continuous function. But what's happening right at x equals 3? So the first thing I'm going to do is I'm going to say, do I have a limit? Is the limit as x approaches 3 from the right of f of x, is that equal to the limit as x approaches 3, sorry, that one's from the left, this one's from the right, of f of x? Are they equal to each other? Because if they're not equal to each other, the limit doesn't even exist. And of course, then we can't have continuity, because continuity says that the value at that point has to be equal to the limit at that point. And if there's no limit, then there's no continuity. So let's take a look at this. From the left, so this is the first condition, x less than or equal to 3. As x gets closer and closer to 3, and oh, look here, I've got some bad notation going on, because it's not f of x I'm looking at, it's actually g of x in this case. Be very careful about your notation. So here I go, g of x, as x gets closer and closer to 3, but less than 3, this value, g of x, is approaching 3. All right, what about from the right side? So as x gets closer and closer to 3 from the right side, now this is actually approaching 3 squared, which equals 9. And for sure, 3 is not the same thing as 9. So therefore, there is no limit. Or I should say, more specifically, the limit as x approaches 3 of g of x does not exist. So I do not have continuity for that one. Let's come back over here to Desmos and see how that looks. I'm just going to, I'll do it here. I'll type g of x is equal to, now I'm looking at my first condition is x less than or equal to 3. And I want to follow the rule x in that case. Then I'm going to separate the parts of my function with a comma and type in my next condition where 3 is less than x. And the rule that I want to follow there under that condition is x squared. And let's see what this line looks like, what this function looks like. I'm going to turn off this purple. And sure enough, you can see here the g of x, the limit from the left is not the same as the limit from the right. Therefore, the limit itself at x equals 3 as the function approaches x equals 3 does not exist. So there is not continuity. And we can visually see this great big jump in the graph. Okay, hopefully that's helpful. So the next thing I want to do is jump over to problem number, let's see, I think it's problem number 32. So problem number 32 is again looking at piecewise functions. And it says for you to find this unknown value k so that the function is continuous on any interval. So they want you to make a piecewise function that is continuous everywhere. So not just in the interval from 0 to 2 and not just in the interval that's where x is greater than or equal to 2, but everywhere from 0 to x. So in other words, right at 2 itself. So let me bring that back up. And bring up a new page here. So problem number 32 says find k such that f of x equals kx 0 when 0 is less than or equal to x is less than 2 and is equal to 3x squared for 2 less than or equal to x. All right, I'm going to show you how to do this algebraically first. And algebraically, hopefully from the last two examples, what you noticed is that when x equals 2, this condition, this rule here, and this rule here have to result in the same exact value. That way the limit can exist. The limit as x approaches 2 of f of x from the left has to be the same as the limit as x approaches 2 of f of x from the right. And the only way that can happen is that these two values, these two rules result in the exact same value for when x equals 2. So in other words, I need k of x, not k of x, I need 2 times k to be equal to 3 times 2 squared, because I'm finding out when x is 2, what should that k value be. So I have 2k equals 3 times 4, so 2k equals 12, so k equals 6. If k equals 6, then I do have that continuous situation. I want to show you how we could have done that on Desmos. So I'm going to turn this one off. I'm just going to go ahead and delete this one here. And I'm going to type in this f of x. This time is equal to, again, the piecewise function. I give the condition first, 0 less than or equal to x, which is less than 2. And when I have that condition, my rule is kx. Then I'm going to have in my next condition where 2 is less than or equal to k. I'm sorry, less than or equal to x. And I'm going to follow the rule 3x squared when I have that condition. So that's the end of my function. Notice how while I was typing, as soon as I typed in the k, this add slider popped up for k. So I'm going to go ahead and add that slider. And once I do, you can see the function that has been drawn with k equaling to 1. I can play around with k now, and I can see, oh, look at this. As k gets more and more negative, my linear function became a decreasing function, and that's not helpful to me because the limit from the left is not the same as the limit from the right. I can see here as k increases, look at that, I'm getting closer and closer, and now I've gone too far. So only when k is equal to 6 do I have continuity here. So that's a nice way, if you are having trouble, maybe it's a more difficult algebraic expression and you're having trouble finding the value, you can come over here to Desmos and put in your slider and just try different things until you see what the answer should be. Then you can go back over to your paper and work out the algebra and come up with the answer on your paper.